Hello everyone, welcome to this video. Today we're going to talk about the RIPEMD-160 algorithm. This is a hash function that is used in the Bitcoin and cryptocurrencies based on Bitcoin. This hash function is actually based on the MD4 algorithm which we introduced in the previous video. Go check that if you're interested. And let's see how this algorithm works. First, we're gonna do some padding. So suppose that the message has B bits and denoted as M0, M1 until MB-1. First, we're gonna add the bit 1 and several 0 after the original message so that the length will become B prime. B prime is equal to 448 modulo 512. And then we will add another 64 bits B0, B1 until B63. This is the 64-bit representation of B, where B is the length of the original message. And then we will divide it into n words. Well, n here is a multiple of 16. Why we use 16 here is because we're gonna process these message words each time for 16 words of them. This padding process actually is exactly the same as the MD4 algorithm, but for the next process it will different. Let's see. First, we are gonna use 10 MD buffers in this algorithm. We divide it into two sets. The first is A, B, C, D, E, and the second set is A prime, B prime, C prime, D prime, and E prime. And we initialize them by the same initial value A0 to E0, and they're the numbers here. So we initialize the buffers, and now we use them to process the message words. For each of the 16 words, we're gonna process 80 rounds. Well, this 80 rounds consists of 16 rounds, and for the first 16 rounds, the process will be like this. We use the A, B, C, D, E buffers, and which are initialized, and then we use a function f here to take the B, C, D as input and output a value, and then XOR with the value in A, and after that we XOR the message word MI, and then XOR the constant K here, and then we shift the result by S bits to the left, and then XOR with E, and this result goes to B, and the value in B will goes to C. The value in C will also be shifted 10 bits to the left, and then goes to D, and the value in D goes to E, and E goes to A. So this is one of the 16 rounds, and let's check the details here. So the function f here will be defined like this: is B XOR C XOR D, and for each of the 16 round, the MI here is actually M0 to M15, and the constant is set to 0. Here is a hexadecimal number, and then the shift value is set to these numbers for these 16 rounds. Well, after that, let's see the second 16 round. Actually, the calculations are the same, but with different function and different parameters. So the function is defined like this, and the message is not XORed in the order like the first one is in this order. So for the first round in this 16 round, in the M7 will goes here, and then M4 for the next round. And also the constant K here is not 0, and the shifted positions are also different. And we will process the 16 words by all these 80 rounds. Moreover, for these 16 words, we will use the other set of buffers to process them parallelly. So we also process 80 rounds here. Well, the operations in these buffers are also the same as the previous one, but with different functions and parameters here. Well, the details are listed here. So parallelly, we process the same 16 words for 80 rounds of these operations with the details like that. And after that, we're gonna compute E0 by A0 XOR with B XOR with C prime. So A0 here is the initial value we in the initialization process, and B is the result value in the buffer B, and here is the value in the C prime. And also we calculate the A0, B0, C0, and D0 accordingly. Well, to be noted here, we need to calculate E0 before A0 because we need to use the initial value in A rather than this result here. So then we will set both the two sets of buffers by the values A0 to E0 we just computed. And so then we will process the next 16 words of the message, and so we will also process them by these 80 rounds and parallelly by these 80 rounds. And then we will repeat this process until we process all the words, all the N words of the message. And finally, we will output the 160 bits in ABCDE or another set of buffers. They are the same because for each process, we always set them to the same value we calculated. So this is the result of the hash value of the original message. All right, thanks for watching. See you next time.